In our previous lessons, we have seen what is a simple harmonic motions. We have learned how to check whether an object is moving with simple harmonic motions or not. And also we have learned how to calculate the displacement of an object undergoing simple harmonic motions. Today, we are going to look at the velocity, accelerations, and energy of an object undergoing simple harmonic motions. In simple harmonic motions, we can determine the values of these few variables by using time or displacement at a particular point. Now let's see how are we going to determine the velocity in terms of time. In chapter 2, we have learned that velocity at a particular instant can be calculated by using v equals to dx over dt. Thus, equations for linear velocity of an object undergoing simple harmonic motions can also be derived by using same method, which is by differentiating equations of displacement with respect to time. So we have v equals to dx over dt, and we know that x is equals to a sine omega t. So when you substitute x into the equations, you're going to get v equals to d over dt a sine omega t. So this a sine omega t, it comes from this one. Okay, it comes from x equals to a sine omega t. Now we have a trigo functions, and the time is located inside the trigo function. So how are we going to differentiate these equations? So we're going to use substitutions method to solve it. By using substitutions method, we can find out what is the formula for v. So what is substitutions method? So v equals to dx over dt. Now this dx over dt, we can write it as du over dt times dx over du, meaning that you are going to split these equations a sine omega t into two parts. So first, let's assume u is equals to omega t and x is equals to a sine u. So as you can see now, I have t in the formula in the equations for u, and I have u in the equations for x. So meaning that I'm going to differentiate u with respect to time and x with respect to u. So how are we going to differentiate it? Let's go through the basic concepts in the differentiations. So let's say we have u equals to omega t. Now let's assume I don't know what is the powers for t. I'm just going to put an n here. So if you differentiate omega t, okay, you differentiate u with respect to time, what's going to happen? So you're going to take this power n to the front. So you have n, and then you just have to rewrite omega t here with the power of n, but now you have to minus 1. So this is how you differentiate the variables, okay, and equations. So this is a part for the u equals to omega t. Then how about sine? So when you differentiate sine, okay, when you differentiate sine, you're going to get, let's say you differentiate sine x, you're going to get cos x. And when you differentiate cos, you're going to get negative sine x. This is very important, yeah? You must know. Why? Because sometimes the questions won't give you x in terms of sine functions. Sometimes questions will give you x equals to a cos omega t. So you have to know that. You have to know what to do if the questions give you cos functions. So if you have x equals to a cos u, then after you differentiate x with respect to u, you're going to get x dx over du equals to negative a sine u. Okay, if the questions give you the cos function. But now we're just going to go back to our questions, where we have u equals to omega t and x equals to a sine u. So if you derive it, okay, after you differentiate it, you're going to get du over dt equals to omega, dx over du equals to a cos u. So you differentiate sine, you get cos. Okay, a you just keep it. Why? Because a, it has nothing to do with u. So if you want to differentiate with respect to u, you just differentiate the part that come with the variable u. So a, it doesn't consist of u, so you can just write it down. It's just a value, a constant. So you differentiate sine, you get cos. So if you are given a cos function here, after you differentiate, it becomes negative sine. Then I'm just going to times them together. So v equals to du over dt times dx over du, which will give you v equals to a omega cos omega t. Okay, so why cos omega t? Because this one, okay, is equals to u. So you just replace u equals to omega t back to your equations after you times them together. Okay, so v equals to a omega cos omega t. So this is the equations in terms of time. Okay, this is the equations in terms of time. Now that we have the velocity in terms of time, next we're going to derive an equations for velocity in terms of x, in terms of displacement. Okay, so when we say in terms of displacement, means that in our equations, we want to exclude the time. We don't want the times anymore. So since we want it in terms of displacement, let us begin with the general equations for displacement. So from equations, x equals to a sine omega t. If you arrange the equations, you're going to get sine omega t equals to x over a. So what I'm going to do next, I'm going to square both sides. Okay, I'm going to square both sides. Why? Because I will try to remove the sine omega t part by using trigo identity method. So after you square both sides, you're going to get sine square omega t equals to x squared over a squared. And since we are going to derive an equations for velocity, of course, we are going to need the equations for velocity. So we have v equals to a omega cos omega t. Now what am I going to do next? Same thing. I'm going to square both sides. Okay, I'm going to square both sides. So after you square both sides, you're going to get v squared equals to a squared omega squared cos squared omega t. This would be the second equations that we have. So equations 1, equations 2. Now that you have two equations, what are you going to do next? You're going to apply trigo identity relationships. Okay, equations. So from trigonometry identity, we know that cos omega t plus sine omega t equals to 1. Well, which is cos square theta plus sine square theta equals to 1. So you rearrange the equations. Okay, then you're going to get cos square omega t equals to 1 minus sine square omega t. I'm going to call this equations 3. Okay, I'm going to call this equations 3. So you substitute this 3 into 2. Okay, you substitute this one into our second equations. So meaning that this part, we want to remove it. Okay, we are going to replace it with this part. Why? So that after this, we can put our equations 1 into our new equations. So we have v squared equals to a squared omega squared bracket 1 minus sine squared omega t. I'm going to call it equations 4 for now. So after you have equations 4, what are you going to do next? You still have omega t in your equations. So you are going to remove it by using equations 1. Okay, you're going to remove it by using equations 1. Substitute 1 into 4, you're going to get v squared equals to a squared omega squared bracket 1 minus x squared over a squared. So this x squared over a squared, it comes from your sine squared omega t, which is from your equations 1. So when you reach this step, the rest basically becomes very simple. Why? You just have to simplify the equations. So how are you going to simplify it? The first step is to make sure these two things, okay, these two quantity, they have the same denominator. These two values, they have the same denominator. Okay, now you have 1 minus x squared over a squared. So you have to make sure 1 also have the same denominator as the other one. So 1 is actually equals to a squared over a squared. Okay, and then you substitute into the equations, you're going to get v squared equals to a squared omega squared bracket a squared minus x squared over a squared. Now if you notice, this a squared, the denominator can be cancelled out by a squared outside the bracket. So after you simplify the equations, you're going to get v squared equals to omega squared bracket a squared minus x squared. And after that, you just have to rearrange the equations. After you rearrange the equations, you got plus minus square root omega square a square minus x square. As you can see now, this equation it now doesn't have any t. Okay, it doesn't depend on time anymore. It depends on the displacement, just the displacement. Okay, and one thing that is very important, remember to include this plus minus sign in your equations. Why? So for example, now you have an object. Okay, we know that this is the equilibrium positions. So when your object is located here, it could either be going up or going down. If it is going up, then you're going to have positive v because this is heading to the right hand side, for example. Now, if it's going back to its original directions, then you're going to have a negative v. So even though the displacement is the same, but depends on the directions of motions, it could have a positive or a negative value. Depends on the directions of motions. Okay, so since now these equations, it doesn't depend on times anymore, it depends on just displacement, we can call it v in terms of the displacement. So we are done with velocity. Now we are going to see how to derive equations for accelerations. In chapter 2, we have seen that instantaneous acceleration is equal to dv over dt. We can do the same for simple harmonic motions. So by differentiating equations of velocity with respect to time, so we got a equals to dv over dt. Based on our derivation just now, we have v equals to a omega cos omega t, right? So you're going to have a equals to d over dt, a omega cos omega t. So this one is your v. Okay, this one is your v. So after you substitute v into the equations, what are you going to do next? Well, you're going to differentiate the trig functions. So meaning that you're going to apply substitutions method again. So I'm not going to show you again. Okay, you try it by yourself. If you do it correctly, you're going to get a equals to negative a omega square sine omega t. Small letter a is the accelerations, capital letter A is the amplitude. Don't mix up these two a. Okay, now if you look at the equations, you have a negative sign here. Why? So if you remember what I told you just now, okay, when you differentiate sine, omega t, you're going to get cos omega t. If you differentiate cos omega t, you are going to get negative sine omega t. Okay, and since your v has a cos functions here, your v is in terms of the cos omega t. After you differentiate cos omega t, you're going to get negative sine omega t. So this is the equations in terms of time. Now how about equations in terms of displacement? It's very simple. Okay, this one is not as complicated as a velocity. If you look at these equations, you have a equals to negative a omega square sine omega t. And we know that x is equals to a sine omega t, right? So you compare these two equations, okay, you compare these two equations, this one and this one, what are you going to see? You have a here, you have sine omega t here, right? So basically, a is equals to negative omega square x. Why? Because if you rearrange the equations above, you're going to get a equals to negative omega square bracket a sine omega t. And a sine omega t is your x. Okay, it's your x. So this one is the acceleration in terms of displacement. So if you notice, accelerations in terms of time, there's no x in the equations, whereas for the accelerations in terms of displacement, there's no t in the equations. Okay. Next, we are going to derive the equations for various types of energy. So let us start from kinetic energy. So from the kinetic energy equations, we have k equals to half mv squared. So in order to derive the kinetic energy in terms of time, you just have to substitute the v in terms of time. So if you want to derive the equations for k, kinetic energy in terms of displacement, then you just substitute v in terms of displacement. So for kinetic energy in terms of time, okay, let us substitute v equals to a omega cos omega t, because this is the v in terms of time. So you substitute it into the equations, you're going to get k equals to 1 over 2 m omega square a square cos square omega t. This is kinetic energy in terms of time. So for kinetic energy in terms of displacement, you substitute v in terms of displacement. So after you substitute into the equations, you're going to get K equals to 1 over 2 m omega bracket a square minus x square. So this is the kinetic energy in terms of displacement. Let's do the same for potential energy. So from potential energy equations, we have U equals to half kx squared. This is the energy stored in a spring. So if you want to calculate potential energy in terms of time, what you're going to do, you just have to replace this x with the x in terms of time. So substitute x equals to a sine omega t. You have U equals to 1 over 2 ka square sine square omega t. This is the potential energy in terms of time. For potential energy in terms of displacement, if you look at the equation itself, you have U equals to half kx squared. This equation is already in terms of displacement x. So meaning that you can use these equations straight away to calculate the potential energy for simple harmonic motions if you are given k. Now, what if you are not given k? You have another options. If you look at the equation for accelerations for a spring, for an oscillating spring, you have a equals to negative k over mx. And based on the general equations that you derived just now, you have a equals to negative omega square x. So when you compare these two equations, you will see that k over m is actually equals to omega square. Rearrange the equations, you're going to get k equals to m omega square. Now you substitute k equals to m omega square into the equation for potential energy. You're going to get U equals to 1 over 2 m omega square x omega square. This is another equations in terms of displacement. So now you have two equations to calculate the potential energy in terms of displacement. Now that you have kinetic energy and potential energy, you can then calculate the total energy in a simple harmonic motions. So total energy E is equals to K plus U. So E is equals to half m omega square bracket a square minus x square plus half m omega square x square. Simplify the equation, you will get E equals to half m omega square a square. As you can see here, this equation, it does not depend on times or displacement. So it can be used for both. So just now we have also seen that K is equals to m omega squared. Therefore, these equations can be written as E equals to half ka squared. Okay, so it doesn't depend on time, no displacement. So it can be used in both situations. Let's see what is the relationship between energy and amplitude. According to the conservations of energy, summations E is equals to K plus U, and it is always equals to a constant value if there's no energy loss. So in our syllabus, we assume there's no energy loss in an oscillation. Let's look at this diagram. If you release an object at its maximum displacement, okay, this is x equals to maximum. So there's no velocity. Why? Because velocity is always equals to 0 at the turning point, at the maximum point. So v is equals to 0. Therefore, we have k equals to 0 here. And our u, our energy, is at its maximum value, which is equals to the total energy. Okay, therefore you have these two. Okay, these two, they have the same value. So when the object moves until its equilibrium positions, where we assume x is equals to 0, and at this point the velocity is at its highest value. So v is equals to maximum value. So at these positions, when the object is at its equilibrium positions, we have u equals to 0. And according to this diagram, this bar chart, our kinetic energy is now at its maximum value, okay, which is equals to the total energy. So let's go to the negative amplitude. We have again k equals to 0 because it is at its turning point, and u is equals to total energy, u is equals to the maximum value. And when it goes back to these equilibrium positions again, we have u equals to 0, k equals to max. It keeps going on. And what if it is located in between equilibrium positions and the maximum point? Then you have to look at the x. Okay, you use x to calculate their value. So k is not equals to 0 and is not equals to the maximum value. And u is also not equals to the 0 and not equals to maximum value. But when you add them up, they are still going to have the same total energy. E is still going to be the same as the other positions. So this is the meanings of E is constant in an oscillations. Now let's put the equations that you derived just now in a table. So when you put them all into the table, this is what you're going to get. The equations in terms of time and the equations in terms of displacement. Then how about the maximum value? Maximum value actually is very simple. You look at the equation for x. In terms of times, you have a sine omega t. Maximum value for sine omega t is equals to 1. Therefore, maximum x is equals to a. For v, you have a omega cos omega t. When the v is at its maximum value, we have cos omega t equals to 1. Therefore, you have a omega. Whereas for accelerations, you have negative a omega squared sine omega t. In order to obtain maximum value, once again, we're going to take maximum sine omega t, which is equals to 1. Therefore, maximum acceleration is a omega squared. For ku, the maximum value is just equals to e, therefore I didn't put it down here. So e is already the total value, therefore I'm not going to put it down as well. So that's all for today. If you have any questions, you may ask in the class